Assalamualaikum and good day to our lecturer and fellow students. In this video, our group will be presenting the growth of population in Monaco from 1980 to 2000. First of all, let's look at our team members who have been working hard for this project. Firstly, my name is Muhammad Faizuddin. Next, we have Muhammad Afiq Aiman, Nur Amna Hazikah, Rania Anissa, Imelda Shazlin, and lastly, Wan Nur Husna. Now, let's look at a bit of an overview about this project. To begin with, we applied the first order differential equations to model and predict the population trends of Monaco. We make use of the exponential growth model as shown here. We also include a set of data for the actual population of Monaco over the same period of time from worldometer to ensure the accuracy of our work. Without further ado, let's pass this stage to the next presenter and look at the next step.
Next, this table presents the population data of Monaco from the year of 1980 to the year of 2000. The actual population column shows the recorded data, while the predicted population is obtained using a mathematical model based on a particular solution. From the data, we can clearly observe a steady increase in population over time, rising from 37,122 in the year of 1980 to 32,455 in the year of 2000, which indicates a consistent growth trend. When comparing the actual and predicted values, the model appears to follow the general pattern closely, especially in the earlier years, although small differences become more noticeable as time progresses. This suggests that while the model is reasonably accurate, although it may not fully capture real-world factors. Overall, this data provides a useful basis for developing and evaluating a mathematical model to predict population growth, which will be explained further in the next part.
First, we start with the differential equation dp over dt equals to kp. We separate the variables by moving p to one side and t to the other side. So we get 1 over p dp equals to k dt. Next, we integrate both sides. The integral of 1 over p dp gives us natural log of p, and the integral of k dt gives us kt plus c, where c is a constant. Then we rewrite the equation in exponential form, and we get p equals to ae to the power of kt, where a is a constant. For the step 2, we use the initial condition. When t equals to 0, p equals to 27,122. Then we substitute the value of p and t into the equation. 27,122 equals to ae to the power of k times 0. Since e power 0 equals to 1, we get a equals to 27,122. So our general equation becomes p equals to 27,122 e to the power of kt. For the final step, we find the value of k. We use another condition. When t equals to 1, p equals to 27,293. Then we substitute the value of p, a and t in the equation. 27,293 equals to 27,122 e to the power of k times 1. Then we divide both sides. E to the power of k equals to 27,293 divided by 27,122. Finally, we get k is approximately 0.006285. So our particular solution is p of t equals to the 27,182 e to the power of 0.006285 t.
Right now, I will be explaining the graph of population growth in Monaco from 1980 to 2000. This graph shows two sets of data. The blue line represents the actual population, while the black line represents the population predicted using the particular solution. From the graph, we can see that both lines show an increasing trend, which means the population of Monaco generally increased over time. However, the blue line is consistently higher than the black line, especially after the early 1980s. This means that the actual population grew faster than what our mathematical model predicted. There are a few reasons for this difference. The model assumes a constant growth rate, but in reality, population changes due to factors like migration and economic conditions. These real-life factors can cause the actual population to grow faster than predicted. Therefore, while the particular solution provides a good general estimate of population growth, it is not perfectly accurate because real-world population changes are more complex and do not follow a fixed exponential pattern.
Next, we move to the analysis and discussion of our population study. Question number 1. We check whether the calculated values from our model are consistent with the actual values. The answer is no, because there are differences between the calculated and the real data. For question number 2, we calculate the percentage error using the formula difference between actual and calculated values divided by actual values times 100. For 1979, the error is about 0.22, which is very small, but in 2001, the error increases around 4.63, showing the model is less accurate over time. Next, for the question number 3, the difference happens because our model is linear, meaning it assumes population increases at a constant rate. However, real population growth is usually nonlinear, often following exponential or logistic patterns. This means the growth rate changes over time, causing fluctuations that our model cannot capture. Next, we move to the question number 4. What factors have influenced population growth or decay in the past? When we're looking at how a population changes, we first have to understand what happened in the past. Improved healthcare was a major factor because in the past, simple things like vaccine and better medicine mean that people live much longer, and more children grew up to have families of their own. This created a steady climb in number that we can see in almost every historical model. Another big reason was net migration, which is just the movement of people moving from one place to another in search of better job or safety. And finally, economic prosperity helped population grow because as countries got wealthier, they had more resources to support more people. Next, we move to the question number 5. What factors have influenced population growth or decay in the future? Looking forward, the factors that will affect the future are different. We have to think about resources constraint like whether there is enough food and water for everyone. Government policies also play a huge role as laws about family planning or immigration can quickly change the numbers. And lastly, technological shifts like new invention or changes in how we work will change how many people an area can support. By looking at these past and future points together, we can better predict how our work will change.
To wrap everything up, our project has shown that we can actually use first-order differential equations to track how Monaco's population changed over those 20 years. By calculating the growth constant k at 0.006285, we were able to build a mathematical model that mirrors the actual population trends of the era. Additionally, we can be confident in this model because the percentage errors were low. Our past prediction for 1979 had an error of only 0.22%, while our future predictions for 2001 stayed within a reasonable 4.62%. As we have noted in our discussion, maths sometimes assume a very steady and fixed path. However, the real world is a bit more unpredictable than that. Things like better healthcare, migration, and the economy all play a part in those small differences we found. Despite these variations, our project proves that mathematical modeling is an essential and effective tool for understanding and forecasting demographic patterns. That's all from us. Thank you.